Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Certain problems in science possess a peculiar gravity. They loom over a discipline, their mass warping the very fabric of research around them, pulling generations of brilliant minds into their orbit. At the dawn of the 20th century, the chemical structure of cholesterol was such a problem. This waxy, crystalline substance, isolated from gallstones and present in every animal cell, was an enigma of the highest order. Chemists had mastered the art of analyzing and synthesizing smaller, simpler molecules. They could assemble dyes, fragrances, and medicines with growing confidence. Cholesterol, however, with its hefty formula of C27H46O, represented a different class of challenge altogether. It was a monolith from the world of biology, and the tools of classical organic chemistry, when applied to it, behaved with a frustrating lack of finesse. The prevailing methods for structural elucidation were exercises in controlled destruction. A chemist would take a large, unknown molecule and subject it to harsh oxidizing agents, like potassium permanganate or chromic acid. The hope was that the molecule would cleave at its weakest points, breaking into smaller, recognizable fragments. From this collection of molecular debris, one might piece together the architecture of the original compound for many natural products. This approach worked. With cholesterol, it was a catastrophe. The molecule resisted degradation with a stubborn integrity, and when it finally succumbed, it shattered into a bewildering spray of small, acidic compounds that offered few clues to the parent structure. The process was akin to determining the floor plan of a palace by studying its demolition dust. The information was there, somewhere, but scrambled beyond recognition. For decades, the world's finest organic chemists wrestled with this puzzle. The great Adolf Windaus at the University of Göttingen dedicated much of his career to the sterols, performing a heroic volume of degradative experiments. His laboratory produced a mountain of data, yet the central question of the molecule's core skeleton remained elusive. The proposed structures, including Windaus's own, were clever, yet ultimately incorrect, artifacts of a methodology ill-suited to the task. The field was mired in a state of elegant confusion, rich with experimental results that pointed in contradictory directions. A new philosophy was required, a technique of chemical archaeology that could scrape away the obscuring layers of a molecule without destroying the fundamental structure buried beneath. This new philosophy found its champion in Otto Diels, a product of the University of Berlin and a student of the legendary Emil Fischer. Diels was an inheritor of a powerful intellectual tradition. Fischer had achieved the seemingly impossible by unraveling the structures of sugars and purines, vast and complex molecules for their time. His success was built upon a foundation of meticulous patience and the development of reactions that were specific and gentle. He taught his students that to understand a complex biomolecule, one must learn to dissect it with a scalpel, avoiding the chemical hammer. This principle became the core of Diels' own scientific worldview. He approached the cholesterol problem with the conviction that a gentler path must exist. His profound insight, arriving after years of contemplation, was to reimagine the problem entirely. He sought a transformation that would preserve the carbon skeleton while making it easier to analyze. He theorized that the core of cholesterol was a polycyclic system of saturated, hydrogen-rich rings. These rings, known as allocyclic structures, were notoriously difficult to characterize. Aromatic rings, like benzene, were by contrast flat, stable, and possessed a wealth of well-understood chemical reactions. Diels' brilliant conceptual leap was this: what if one could cleanly strip all the extra hydrogen atoms from cholesterol's core, forcing the saturated rings to collapse into a single, stable, aromatic system? Such a process, a dehydrogenation, would act as a chemical X-ray, revealing the fused ring skeleton in a simple, analyzable form. The challenge was finding the right reagent. It needed to be powerful enough to abstract hydrogen atoms at high temperatures, yet selective enough to leave the carbon-carbon bonds of the skeleton intact. After considering various possibilities, Diels settled on an element from the oxygen family, selenium. Heating an organic compound with a gray, metallic-looking powder seemed a crude and unpromising affair. Yet, in Diels' hands, it was an instrument of sublime precision. In a landmark experiment, first published in 1927 in the paper titled Über die Dehydrierung des Cholesterins, Diels and his colleagues heated cholesterol with selenium powder in a CO2. As the temperature climbed past 300 degrees Celsius, the selenium performed its function with remarkable efficiency. It plucked hydrogen atoms from the steroid nucleus, releasing them as hydrogen selenide gas. The saturated rings, shedding their hydrogen, flattened, and rearranged their bonding to achieve the profound stability of an aromatic system. When the reaction vessel cooled, Diels isolated a new, crystalline hydrocarbon. This compound was the key. Its structure was simple enough to be determined unequivocally by synthesis and spectroscopic analysis. It was a phenanthrene nucleus, a system of 3 fused 6-membered rings with a 5-membered ring fused to it. The molecule, 3-methyl-1,2-cyclopentranolphenanthrin, immediately became known throughout the chemical world as Diels hydrocarbon. Its discovery was a moment of supreme clarification. It provided the first piece of irrefutable physical evidence for the true four-ring structure of the steroid nucleus. All the years of conflicting data from oxidative degradations were swept aside. Here was the skeleton laid bare. The impact was immediate and transformative. The discovery provided the essential roadmap for the entire field of steroid chemistry. Adolf Windaus, who had labored for so long under Floyd's structural hypothesis, could now reinterpret his vast body of experimental work in light of the correct framework. The new structure explained away old anomalies and brought coherence to decades of research, contributing to the work for which he would receive the Nobel Prize in Chemistry in 1928. The influence extended powerfully to the next generation of chemists. In laboratories across Europe, researchers like Alf Butenandt in Germany and Leopold Rudiger in Switzerland were racing to isolate and identify the sex hormones. These substances, present in minuscule quantities, were structurally related to cholesterol. Diels' hydrocarbon gave them the crucial architectural blueprint. And with this knowledge, Butenandt and Rudiger were able to rapidly deduce the structures of androsterone, progesterone, and testosterone, a feat that culminated in their shared Nobel Prize in 1939. Their monumental achievements in synthetic biology and medicine rested squarely upon the foundation laid by Diels' selenium dehydrogenation. It was a triumph of chemical strategy, a testament to the idea that sometimes the most profound revelations come from a change in perspective and the application of a gentler touch. This success Born of patient inquiry into the secrets of a natural product, prepare the ground for discovery of a completely different character, one that would arise from a moment of pure, unexpected chemical serendipity. The intellectual atmosphere of the Chemical Institute at the University of Kiel in the late 1920s was one of rigorous, classical organic chemistry. Otto Diels, now a mature and respected professor, guided his students through the established canons of synthesis and analysis. His recent triumph with selenium dehydrogenation had solidified his reputation as a master of structural elucidation. Yet, the next chapter of his legacy would emerge from a completely different core, born from an experimental anomaly that lesser minds might have dismissed as a nuisance. The catalyst for this transformation was a gifted and meticulous doctoral student, Diels-Alder, who was working under Diels' supervision. Their collaboration would soon stumble upon a principle of chemical construction so fundamental and elegant that it would forever alter the logic of synthesis. Their investigation began with a familiar problem in the chemistry of conjugated systems. Diels tasked Alder with studying the addition reactions of azidicarboxylic esters to dienes, a line of inquiry that followed logically from the era's fascination with the unique reactivity of alternating double bonds. As a side experiment, they attempted to react cyclopentadiene with benzoquinone. The initial results were frustratingly inconsistent, producing a tarry, unworkable mixture. A common culprit for such polymerization problems was thought to be peroxides lurking in their solvent, diethyl ether. Following standard practice, they sought a more inert medium. The experiment was repeated in benzene, a simple procedural change that unexpectedly yielded a beautiful, crystalline solid. The reaction proceeded cleanly, affording the product in high yield. This crystalline substance was the first clue, the first tangible piece of evidence for an entirely new form of chemical transformation. The structure of this product was perplexing. It failed to conform to any known addition or substitution pattern. A straightforward reaction would have yielded one specific structure. The compound in their flask was something else entirely. It was in the meticulous analysis of this unexpected deduct that the genius of Diels and Alder revealed itself. Through careful degradation and characterization, they deduced that the two molecules had fused together in a remarkable way. The conjugated diene, cyclopentadiene, had acted as a single 4pi electron unit, while the benzoquinone, possessing an activated double bond, had served as a 2pi electron partner. In a single, concerted process, two new sigma bonds had formed, creating a stable 6-membered ring and bridging the two original molecules. They had discovered what is now universally known as the Diels-Alder reaction, a 4+2 cycloaddition. Their seminal 1928 paper, titled Synthesin in der Hydroaromatischen Reihe, or Syntheses in the Hydroaromatic Series, published in the journal Justus Liebig's Alan der Kenny, announced this discovery to a stunned chemical community. The paper was a model of scientific clarity and prescience. It laid out the fundamental principle: a molecule containing a conjugated diene system reacts with a second molecule containing a double or triple bond, which they termed the dienophile or diene motor, to form a 6-membered ring. The beauty of the reaction lay in its profound efficiency and atom economy. Every atom from the starting materials was incorporated into the product. There were no byproducts, no waste. This stood in stark contrast to the often laborious, multi-step, and the low-yielding methods for ring construction that were dominant at the time. It was a new paradigm for building molecular complexity from simple precursors. To demonstrate the power and predictability of their discovery, Diels and Alder presented a series of examples, the most iconic of which remains the reaction between cyclopentadiene and malic anhydride. Malic anhydride, with its two electron-withdrawing carbonyl groups flanking the double bond, proved to be an exceptionally reactive dienophile. When mixed with cyclopentadiene, the reaction proceeded with almost quantitative yield at room temperature, producing a single, crystalline product. This specific example became the crucible for uncovering an even deeper stereochemical principle. The reaction was stereospecific, meaning the spatial arrangement of the atoms in the starting materials was perfectly preserved in the three-dimensional structure of the product. Their careful analysis of the product from this reaction led them to formulate an empirical guideline of immense predictive power, the Endo rule. They observed that the substituents on the dienophile, in this case the anhydride portion of the molecule, preferentially oriented themselves in a specific way relative to the diene. In the transition state, the dienophile tucks itself underneath the arch of the diene, allowing for a favorable secondary interaction between the pi orbitals of the dienophile's substituents and the interior pi orbitals of the diene. This resulted in the formation of the endo-stereoisomer as the major product. This rule, established decades before its theoretical underpinnings were fully elucidated by Frontier Molecular Orbital theory, gave chemists an extraordinary degree of control. They could now predict and dictate the precise, three-dimensional outcome of a complex ring-forming reaction, a level of stereochemical command that was previously the domain of nature's enzymes. While the discovery itself felt like a bolt of lightning from a clear sky, its intellectual heritage can be traced to the theoretical groundwork laid a generation earlier. The German chemist Johannes Thiel, in his attempts to explain the unusual stability and reactivity of benzene and conjugated polyenes, had proposed the concept of partial valences in 1899. Thiel envisioned that the pi bonds in a conjugated system were in a state of flux, leaving residual bonding capacity, or partial valences, at the ends of the system. This allowed the entire conjugated chain to react as a single, coherent unit. Thiel's model was a brilliant, albeit primitive, forerunner of modern resonance and molecular orbital theory. It provided a conceptual vocabulary for Diels and Alder to rationalize their observation. They could see the diene performing as Thiel had imagined, its collective reactivity harnessed in a single, concerted bond-forming event. Their experiment was the ultimate, spectacular confirmation of the cooperative nature of conjugated pi systems. The impact was immediate and profound. The chemical community, recognizing the reaction's fundamental importance, swiftly christened it the Diels-Alder reaction, a rare tribute to its living discoverers. For Diels-Alder, the discovery defined the entire trajectory of his scientific life. He would dedicate his subsequent career to exploring the vast scope and mechanistic intricacies of this single transformation. For the world of organic synthesis, the discovery was akin to being handed a new, powerful, and versatile architectural tool. It offered a direct and elegant pathway to the cyclic systems that form the skeletons of countless natural products, from alkaloids to steroids to terpenes. The immediate challenge then became one of systematic exploration. Chemists needed to map the boundaries of this new chemical continent to understand the rules governing its diverse reactions and to begin harnessing its power for the deliberate construction of nature's own complex molecular masterpieces. The intellectual momentum following the initial 1928 publication was immediate and profound. The chemical community, recognizing the reaction's fundamental importance, swiftly christened it the Diels-Alder reaction, a rare tribute to its living discoverers. For Kurt Alder, the discovery defined the entire trajectory of his scientific life. He would dedicate his subsequent career to exploring the vast scope and mechanistic intricacies of this single transformation. For the world of organic synthesis, the discovery was akin to being handed a new, powerful, and versatile architectural tool. It offered a direct and elegant pathway to the cyclic systems that form the skeletons of countless natural products, from alkaloids to steroids to terpenes. The immediate challenge, then, became one of systematic exploration. Chemists needed to map the boundaries of this new chemical continent, to understand the rules governing its diverse reactions, and to begin harnessing its power for the deliberate construction of nature's own complex molecular masterpieces. This subsequent phase of work, conducted with meticulous rigor by Diels-Alder and their students throughout the 1930s, represented the crucial transition from a singular, astonishing discovery to a robust, predictive, and generalizable principle of chemical synthesis. This was the intellectual heavy lifting required to transform a flash of brilliance into a cornerstone of a discipline. The research program became a systematic cartography of this new reaction space. They began by testing an exhaustive array of dienes and dienophiles, probing the limits of reactivity. They found that the reaction was remarkably general. Acyclic dienes like isoprene and piperine, and cyclic dienes like cyclopentadiene and furan, all participated with aplomb. The true key to unlocking its full potential, they discovered, lay in the nature of the dienophile. Reactivity was dramatically enhanced when the dienophile, the two-carbon component, was activated by the presence of electron-withdrawing groups functionalities like carbonyls, esters, nitriles, or nitro groups that pull electron density away from the double bond. This empirical observation, that an electron-rich diene paired most favorably with an electron-poor dienophile, was a profound clue to the reaction's electronic underpinnings, a pattern that would wait decades for full theoretical explanation. The exploration of its vast scope proceeded in parallel with a deep inquiry into its underlying mechanism. Here, Diels and Alder uncovered the reaction's most beautiful and synthetically useful feature, its exquisite stereochemical control. They demonstrated, through countless examples, that the reaction proceeds through a concerted pathway. This means the two new sigma bonds forming the six-membered ring are created in a single, fluid step. There are no intermediate stages, no charged species that could scramble the geometric information of the starting materials. The reactants approach, coalesce in a highly ordered, cyclic transition state, and emerge as the product, their original spatial arrangements faithfully preserved. This concert of atoms has powerful consequences. The first is that the reaction is stereospecific with respect to the dienophile. If one begins with the dienophile where the substituents are cis, or on the same side of the double bond, the resulting cyclohexene ring will have those substituents in a cis relationship. Likewise, a trans dienophile yields a trans product. The reaction acts as a perfect molecular transfer of geometric information, a quality immensely valuable for a synthetic chemist striving for precision. A second consequence, particularly evident with cyclic dienes, was an observed preference for what became known as the endo product. In the reaction of cyclopentadiene with malate anhydride, for instance, two stereoisomers are possible. The endoisomer, where the larger part of the dienophile is tucked under the newly forming ring, and the exoisomer, where it points away. The overwhelming formation of the endo product suggested a subtle secondary orbital interaction in the transition state, a kind of fleeting electronic attraction that stabilized this more compact arrangement. For Diels and Alder, this was another empirical rule, a reliable prediction that nature, for reasons of its own, preferred one architectural form over another. The culmination of the systematic work was its application to strategic synthesis. The Diels-Alder reaction was an ideal tool for molecular architecture, capable of building complex, polycyclic frameworks with multiple stereocenters in a single, elegant operation. A quintessential illustration of this power emerged in the conceptual approach to synthesizing camphoratin. This molecule, the active irritant in the blister beetle, is a deceptively simple-looking bicyclic ether with a challenging bridged structure. Classical methods of ring formation would require a lengthy, cumbersome sequence of reactions. The Diels-Alder reaction, however, offered a breathtakingly direct route by envisioning a reaction between furan, serving as the diene, and dimethylmalic anhydride as the dienophile. The entire bicyclooctane core of camphoratin could be assembled in one step. The reaction sets the bridged ether linkage and the relative stereochemistry of the methyl groups with absolute control. This single transformation accomplishes what would otherwise demand a half-dozen steps, showcasing the reaction's profound efficiency and strategic elegance. It was a paradigm shift in how chemists could think about constructing complex targets. This body of empirical work, the meticulous mapping of scope and the codification of stereochemical rules, formed the bedrock upon which future theoretical understanding would be built. The consistent stereospecificity, the predictable regioselectivity with unsymmetrical partners, and the curious endo-preference were all deep clues pointing to a fundamental electronic order. Decades later, the work of chemists like Kenishi Fukui and Roald Hoffmann would provide the definitive explanation through the lens of frontier molecular orbital theory. They showed that the reaction is governed by the interaction between the highest occupied molecular orbital, or HOMO, of the diene and the lowest unoccupied molecular orbital, or LUMO, of the dienophile. The symmetry and energy of these frontier orbitals explained everything. Diels and Alder had observed why electron-withdrawing groups on the dienophile accelerated the reaction, why the stereochemistry was perfectly preserved, and even the subtle secondary interactions that favor the endo product. The empirical laws discovered in Kiel and Cologne in the 1930s became the experimental proof for one of the most powerful theories in modern organic chemistry. The direct influence of this established, reliable reaction on the next generation of synthetic chemists was immense and transformative. Perhaps its most brilliant practitioner was Robert Burns Woodward at Harvard University. Woodward, a grandmaster of chemical synthesis, viewed the Diels-Alder reaction as a primary strategic weapon for imposing order on complex molecular scaffolds. In his historic total synthesis of quinine in 1944, a Diels-Alder reaction was employed to construct a key, bicyclic intermediate, establishing a critical ring junction and setting multiple stereois centers with the precision of a master architect. Later, in his monumental syntheses of cholesterol and cornerstone, the reaction was again a pivotal move used to forge the intricate fused ring systems of the steroid nucleus. For Woodward, the reaction was a guarantee of stereochemical fidelity, a way to translate a two-dimensional plan on paper into a three-dimensional reality in the flask with unparalleled control. This elevation of the reaction to a strategic principle also profoundly shaped the thinking of Elias James Corey, the father of retrosynthetic analysis. Retrosynthesis is the art of deconstructing a complex target molecule into simpler, available starting materials. The Diels-Alder reaction represents a perfect retrosynthetic transform. Its high degree of predictability and reliability means a chemist can confidently disconnect a six-membered ring in a target molecule, knowing that the forward reaction, the Diels-Alder cycloaddition, will almost certainly work to reform it. The reaction became a fundamental disconnection in the lexicon of synthetic planning, a reliable move in the intellectual chess game of building molecules. Through the systematic and exhaustive work initiated by Otto Diels and Diels-Alder, a chemical reaction was transformed into a fundamental concept, a part of the very grammar of organic synthesis, shaping how all subsequent generations of chemists would perceive and create the world of molecules. The strategic principle of the diene synthesis also profoundly shaped the thinking of Elias James Corey, the father of retrosynthetic analysis. Retrosynthesis is the art of deconstructing a complex target molecule into simpler, available starting materials. The Diels-Alder reaction represents a perfect retrosynthetic transform. Its high degree of predictability and reliability means a chemist can confidently disconnect a six-membered ring in a target molecule, knowing that the forward reaction, the Diels-Alder cycloaddition, will almost certainly work to reform it. The reaction became a fundamental disconnection in the lexicon of synthetic planning, a reliable move in the intellectual chess game of building molecules. Through the systematic and exhaustive work initiated by Otto Diels and Diels-Alder, a chemical reaction was transformed into a fundamental concept, a part of the very grammar of organic synthesis, shaping how all subsequent generations of chemists would perceive and create the world of molecules. Formal recognition for codifying this new language of chemical construction would eventually arrive, though its journey was circuitous, delayed by the very historical forces that would bring Diels' own experimental career to a devastating halt. In 1950, the Royal Swedish Academy of Sciences announced that the Nobel Prize in Chemistry was awarded jointly to Otto Diels and Diels-Alder for their discovery and development of the diene synthesis. The prize came 22 years after their seminal 1928 publication, a period of incubation that allowed the full, world-altering implications of their work to become undeniable. The Nobel Committee, with its characteristic deliberation, waited until the Diels-Alder reaction had proven itself exhaustively. It had been applied to the synthesis of camphor, to the structural elucidation of steroids, and to the creation of countless complex natural products. Its worth was demonstrated in laboratories across the globe. The award, therefore, celebrated a complete intellectual achievement of the initial discovery, the meticulous exploration of its scope by Alder's doctoral work, and its subsequent elevation into a cornerstone of chemical practice. The language of the citation itself is revealing. The prize was for the discovery and development of the reaction, a phrasing that acknowledges the work as a process of creating a tool, a methodology. The committee honored the establishment of the universally applicable principle for forming six-membered rings with unparalleled control over stereochemistry. This was the creation of a reliable architectural strategy. Before Diels and Alder, building such cyclic structures was often a bespoke, unpredictable affair, relying on harsh conditions and yielding ambiguous mixtures. Their work provided a clean, elegant, and powerful alternative. The cycloaddition was a gift of predictability in the often chaotic world of chemical reactivity. The Nobel Prize of the 1950 was the world's ultimate academic ratification, affirming that the 4+2 cycloaddition was a permanent and indispensable part of the synthetic chemist's toolkit, a fundamental contribution to humanity's ability to construct molecular matter at will. This crowning achievement, however, was set against the backdrop of a profound personal and professional crisis. The rise of the Nazi regime in Germany cast a long shadow over the nation's academic institutions. As director of the Chemical Institute at the University of Kiel, Diels navigated this treacherous period with a commitment to scientific integrity. He maintained his professional and ethical independence from the ruling party's ideology. He used his position to shield colleagues, offering a measure of protection to those who fell afoul of the regime's persecutions. His actions ensured that the chemist Walter Huckel, whose career was imperiled by the political climate, could continue his work. These were acts of quiet defiance, efforts to preserve the intellectual sanctuary of the university amidst a rising tide of political extremism. The ultimate catastrophe for Diels' scientific life arrived from the air. Kiel, a major naval base and home to submarine pens, was a primary target for Allied bombing campaigns during the Second World War. In 1944, a series of devastating raids struck the city, and the Chemical Institute was obliterated. The attack annihilated Diels' laboratory, his extensive personal and institutional library, and a lifetime of accumulated research notes and records. For an experimental scientist, this was a terminal blow. The physical infrastructure for his work ceased to exist. His instruments were reduced to rubble, his chemical stocks vaporized, and the priceless, irreplaceable logbooks containing decades of observations were turned to ash. The war had, in a single night, forcibly ended his career as a practicing research chemist. He was 68 years old, and the prospect of rebuilding from such complete destruction was an impossibility. The problem he faced was absolute. There was no laboratory in which to work, no library from which to draw, and no records from which to rebuild. From the embers of this destruction, Diels forged the final phase of his legacy. Stripped of his ability to conduct experiments, he pivoted from the laboratory bench to the writing desk. He channeled his immense knowledge and pedagogical skill into a new project, one of intellectual reconstruction. He undertook the authorship of a comprehensive textbook, Einführung in die Organische Chemie, or Introduction to Organic Chemistry. This work, became his primary occupation in the final years of his active life. Unable to create new molecules, he dedicated himself to creating new chemists. The book was a distillation of a lifetime of experience, a systematic and lucid exposition of the principles of a field he had done so much to advance. Published in the aftermath of the war, the textbook became a standard in German universities. It served a generation of students who were themselves tasked with a monumental project of rebuilding their nation's scientific and industrial infrastructure. Diels' prose provided a clear and authoritative guide, a stable intellectual foundation in a world that had been torn apart. His influence, once channeled through his research group and his publications, was now broadcast directly to thousands of young minds across the country. In this final act, Diels demonstrated a profound resilience. When the tools of discovery were taken from him, he embraced the tools of education. His textbook stands as a testament to his enduring commitment to science, a final contribution ensuring that the knowledge he possessed would be transmitted to those who would build a future. His journey through the mid-20th century thus traces a dramatic arc from the quiet triumph of discovery to the global recognition of the Nobel Prize, through the utter devastation of war, and culminating in a final, powerful act of scholarly service throughout the intellectual inheritance Diels bequeathed through his textbook and foundational papers found fertile ground in a world eager for new chemical frontiers. The Diene synthesis, elegant and robust, became a cornerstone of organic chemistry pedagogy and practice. Yet, its journey was far from complete. The reaction, as originally formulated, possessed a beautiful symmetry that, for later generations, represented a profound challenge. When reacting natural starting materials, the Diels-Alder reaction yields a racemic mixture, an equal 50-50 blend of both possible mirror image molecules or enantiomers. For the structural chemists of Diels' era, this was a minor detail. For the burgeoning field of pharmacology in the late 20th century, it was a critical bottleneck. The biological machinery of the human body is exquisitely chiral. A drug molecule with the correct handedness might save a life, while its mirror image could be inert or, in some cases, actively harmful. The problem, therefore, became one of control how to persuade the diene and dienophile to assemble into one specific enantiomer, breaking the reaction's inherent symmetry. The solution emerged from the field of asymmetric catalysis, a domain pioneered by figures like E.J. Corey at Harvard. Corey recognized that one could introduce a chiral influence into the reaction environment. Its development of chiral acid catalysts, particularly the elegant oxazaboralidine catalysts, provided a watershed moment. These molecules act as chiral directors. The catalyst temporarily binds to the dienophile, creating a three-dimensional pocket with a distinct topography. This pocket effectively shields one face of the dienophile from the approaching diene, ensuring the cycloaddition can occur from only one direction. The result is an enantiomerically enriched product, with one mirror image form produced in vast excess. This conceptual breakthrough transformed the Diels-Alder reaction into a precision instrument for modern medicinal chemistry. Its application is widespread in the synthesis of complex natural products and pharmaceuticals, including steroids, prostaglandins, and antiviral agents, where absolute stereochemical control is paramount. The work of Corey and others built directly upon the foundation laid by Diels and Alder, refining their powerful tool to meet the exacting demands of molecular medicine, while chemists perfected the practical control of the reaction. A parallel revolution was occurring in the theoretical understanding of its mechanism. For decades, the remarkable efficiency and stereospecificity of the diene synthesis were explained by empirical rules and observations. A deeper, quantum mechanical rationale remained elusive. The definitive explanation arrived through the work of Kenichi Fukui in Japan and Roald Hoffmann in the United States. A Frontier Molecular Orbital theory, or FMO theory, for which they shared the Nobel Prize in 1981, provided a beautifully simple and predictive model. The theory posits that the course of a paracyclic reaction, like the Diels-Alder, is governed by the interaction between the highest energy occupied molecular orbital, the HOMO, of one reactant, and the lowest energy unoccupied molecular orbital, the LUMO, of the other. For the reaction to proceed smoothly, these frontier orbitals must have compatible symmetry and be close in energy. Fukui and Hoffmann's framework explained with stunning clarity why the 4+2 cycloaddition works so well, why it proceeds with such high stereoselectivity, and even predicted which reactions were thermally allowed and which were forbidden. This elevated the reaction from a powerful empirical tool to a predictive science, allowing chemists to design novel diene syntheses with a high degree of confidence. The theory provided the intellectual scaffolding that explained the magic Diels had first witnessed in his flask. The ultimate testament to the reaction's enduring power is its migration from the chemist's flask into the living cell. In the early 21st century, the field of chemical biology sought methods to study biomolecules in their native environment without disrupting delicate cellular processes. This required a new type of chemistry termed bio-orthogonal chemistry, capable of forming covalent bonds rapidly and selectively amidst the complex aqueous milieu of life. Carolyn Bertozzi at Stanford University recognized that a variant of the Diels-Alder reaction possessed the ideal characteristics. The inverse electron demand Diels-Alder reaction, which involves an electron-rich dienophile and an electron-poor diene, proceeds with exceptional speed and specificity, and its components have no reactive counterparts within biological systems. By attaching one part of the reactive pair, such as a strained alkyne, to a sugar molecule, Bertozzi could feed these sugars to cells, which would incorporate them into proteins on their surface. Then, by introducing the other reactive partner, a tetrazine attached to a fluorescent dye, she could initiate a rapid 4+2 cycloaddition directly on the cell surface. This click reaction covalently links the dye to the protein of interest, allowing for its visualization with stunning clarity. This work, for which Bertozzi shared the 2022 Nobel Prize in Chemistry, represents the apotheosis of Diels' discovery. The fundamental topology of the 4+2 bond formation, first observed in a simple hydrocarbon reaction, now serves as a sophisticated tool for illuminating the very processes of life. Otto Diels' career, viewed in its entirety, presents a compelling portrait of the scientific mind at its most effective. His legacy is a duality of intellectual character. On one hand, we see the meticulous, almost obsessive analyst, the chemist who spent over 2 decades painstakingly degrading cholesterol with selenium, piece by piece, to reveal its thin sterile core. This was a war of attrition against chemical complexity, won through sheer persistence, systematic rigor, and an unwavering belief in the power of degradative analysis. It was the work of a master craftsman, a scholar committed to the slow, deliberate accumulation of evidence until an irrefutable truth emerged. Simultaneously, we witnessed the creative genius, the mind capable of the profound, intuitively. This is the Diels who, upon observing an unexpected reaction between cyclopentadiene and malate anhydride, immediately grasped its universal significance. He perceived a general principle of synthesis where others might have seen a mere curiosity. This discovery was an act of profound chemical imagination, recognizing a pattern of reactivity that would unlock countless new molecular architectures. His career thus embodies the twin pillars of scientific progress: the relentless discipline of analysis and the imaginative leap of synthesis. He could both take molecules apart with methodical precision and put them together with creative brilliance. The trajectory of the dying synthesis itself mirrors the expansive nature of his insight. It began in a laboratory in Kiel, a city struggling to recover from one world war and soon to be devastated by another. It was a discovery born of serendipity, but nurtured by intellect. A reaction whose utility was immediately apparent. From that flask, its influence spread, first enabling the synthesis of complex natural products and confirming the structures of molecules like camphor. It then evolved, becoming a precision instrument in the hands of pharmaceutical chemists designing life-saving drugs. Its principles were codified by the language of quantum mechanics, transforming it into a predictive science. And finally, in its most modern incarnation, it has become a delicate probe for visualizing the molecular dance of the living cell. This incredible journey, from a simple cycloaddition to a tool for understanding biology, was made possible by the foundational insight of a chemist who possessed the rare ability to see the profound in the particular, and the universal in the unexpected.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.